Great. Thanks, Nikita, for the introduction. Thank you all for sticking out till the last talk today. My name is Aryeh. This is a joint work with my student, Ariel Avital. Okay. Actually, our setting, this paper isn't even about machine learning. It's about decision theory. So setting is, I'll first describe a more basic problem, just so we get the full setting, and then I'll describe the more general one. So imagine that there is a ground truth, which is a bit, which is a random bit, drawn from a balanced Bernoulli, and we want to know why, but we don't have direct access to it. Instead, we have n experts, which are also Bernoulli random variables that are conditionally independent given y, and each one gives the correct advice with probability pi, right? So suppose you know all of these PIs of all the experts, and you also observe. So you both observe their votes and you know their competence levels. How would you aggregate these n bits of advice into a single decision procedure to minimize the probability of error? This is a classic problem. I'm sure you've all seen this. The answer is to do a weighted majority vote where you turn each expert into a signed bit. So this turns a 0-1 bit into a -1 bit, and you weight it by the log odds. This expression is the log odds of the ith expert being correct. This is an easy consequence of the Neyman-Pearson lemma. It's really a simple exercise. This function here, this log odds function, has a very natural behavior. So it's 0.5, which makes sense. An expert that flips a coin is worth nothing, doesn't add anything. And it goes off to infinity as x approaches 1, and it goes off to negative infinity as x approaches 0, which means that experts that tend to give the wrong advice get a very large negative weight. So they're useful. We just have to flip the sign. So it makes sense. Okay, that's the sort of plain vanilla setting. Now let's make things a little bit more interesting. Let's let the ground truth be, drawn from a Bernoulli where the probability is theta. For this talk, I'll take theta to be 1/2, but in the paper, we handle the general case. And again, we have expert advice, but this time I'm allowing asymmetric errors. So the ith expert is, when the ith expert says 1, he's correct with probability psi, and when he says 0, he's correct with probability ati. So there are these, false positive, false negative errors, or as we'll call them here, psi is the sensitivity and ati is the specificity. Right? So if you always say 1, you have great sensitivity but terrible specificity, and vice versa. So you want them both to be large. And yeah, on the previous slide, it was the symmetric setting. So in the symmetric setting, psi equals ati equals pi. That was the previous slide. So here I'm allowing more general errors. And again, you know these parameters. You know the psi and the ati, and you get to observe these n bits of advice. How do you aggregate them into an optimal decision procedure? And again, this is classic. Again, Neyman-Pearson. It's some kind of a weighted majority vote. You turn these bits into signed bits, and you weigh them by these functions, these simple functions of the parameters. So that's all classic. The question that we study in this paper is, what is the behavior of the probability of the optimal procedure of the error probability of optimal decision procedure? So if you follow this formula, if you predict based on this formula, what will your probability of error be? How will it behave? That's the thing that we study in this paper. So I'll begin by giving an exact characterization of this probability of error. And for that, I'll give a very simple natural definition. So for a vector of parameters, so P is a vector in 0, 1, n. It's a vector of n Bernoulli parameters. We turn it into a product distribution. So we take the Bernoulli measure of reduced by P1, by P2, by Pn, take their product. So that gives us a joint probability measure on n bits, or a measure on the binary hypercube, on the discrete hypercube. It's a product measure. Okay, so any vector of n numbers between 0 and 1 induces a product measure on the binary hypercube, like this, right? And recall that we have a ground truth bit, which is Bernoulli half, and a sequence of random bits, conditionally independent given y, where so they're either Bernoulli with parameters psi, or they're Bernoulli with probabilities 1 minus 8i. And that depends on what the value of y is. Okay, that's our setting. And there's a very simple expression that captures exactly the probability of error. It's this. It's I take the product measure p. So these psi's, right? These psi's are a vector of 0, 1 parameters. I turn them into a product measure. So this p is a product measure on the binary hypercube. I take q to be the binary measure induced by 1 minus eta. So I take these sensitivities eta, turn them into a product measure like this, 1 minus eta, right? So I flip them because it's the other setting, and that's my measure q, right? And now I take p and q and I wedge them. And what is wedge? Wedge just means take the pointwise minimum value of the two distributions, and I sum. So compute the L1 norm of that pointwise minimum, right? And that is exactly or half of that is exactly the probability of the error of the optimal procedure. This quantity is actually, it's an interesting quantity. We'll discuss it later. I'm calling it Sheffy affinity. I've also seen it called statistical similarity. It's basically 1 minus the total variation distance. We'll discuss it later. Okay, but this result, and again, it's a consequence of the Neyman-Pearson lemma. Gives an exact expression in terms of the for the probability of error. Now, the thing that's what's satisfying about this result is how simple and intuitive it is. What's unsatisfying about it is that it's hard to compute. Right? The sum is exponential. The sum is not something you can compute efficiently. And not only is it hard to compute naively, just by listing out these two distributions and summing their pointwise minimum, actually it's sharply hard. If you know a little bit of complexity theory, it's a sharply hard problem. So if I give you these two parameters, these two vectors of parameters, and ask you to compute this function of these two n-dimensional vectors, that's a sharply hard problem. There are various polynomial time approximation schemes. It's an active area of research. This is all very recent results. So it would be very nice if you could give a simple analytical estimate on this quantity, which is hard to compute. Okay, so let's do that. So recall that for the reasons above, we are interested in estimating this quantity, this L1 norm of the wedge product of two of the wedge, these L1 norm of the pointwise minimum of these two product distributions, this Sheffy affinity, and an upper bound, a simple upper bound looks like this. So I take the specificity, the sensitivity and specificity, I average them. This is called the balanced accuracy, and I take the product pi I times 1 minus pi I square root and multiply by 2 to the n minus 1. Let's do a sanity check. Let's do a couple of sanity checks. The worst case is when these pi i's are half. When they're half, each expert is worthless. And in that case, this comes out to be exactly two, let's see, so this is a quarter, so, right, square root of that is a half, so this is 1/2 to the n, this is 1/2 to the n minus 1, so what you're left with is exactly a half. And that's the right value. That's the, so you could always get a probability error of a half just by flipping a coin. So you'll never do worse than half in the optimum, right? So in the extreme case where all the pi's are half, this gives you the exact correct value. And likewise, if one of them is 0, so if just one of them is 0, if just one of them is perfect, recall that this log odds weighting, if one of them is perfect, it gives weight infinity to the correct expert. So it just overtakes all the other experts. And if one of them is 0, the probability of error actually becomes 0, because one perfect expert is enough to drive the error down to 0. So it passes these two sanity checks at the extremes. Okay. Now let's look at the lower bound, or at a couple of lower bounds for this quantity. So again, we're looking at the two product measures, P and Q, and their pointwise minimum, and this L1 norm. And it's an expression that looks, this part is identical to the previous, to the upper bound. We picked up this strange-looking factor. So this gamma is the log odds of the balanced accuracy of the ith expert, and this thing in the exponent is just its L1 norm. Okay, so again, this passes the sanity checks that if one of the pi's is 0, this whole thing dies, and this whole thing becomes 0, and if they're all half, this again becomes a half, which is the right value. And in general, this sort of, if you ask, which is the tight bound, so which is the correct bound? Is it the one with this factor or without this factor? So the answer is neither. You can't remove it. You can't not remove it. It's just there's a gap that's actually very, very vexing, but it's real. So if you want a tighter bound, you need something else. Actually, the lower bound can be refined in the case of symmetric errors. So symmetric just means that, as I said before, that the specificity and the sensitivity and the specificity are equal. So if C is equal to eta is equal to P, then I can get a better bound. So this is the same as before. 2 minutes, wow, okay, sure. And this is now the L2 norm of W. L2 is better than L1 because it's smaller than L1, and we're in the exponent, and there's a minus sign, it's lower bound, so actually this is a sharper bound. Again, sanity checks, it passes the sanity checks. Let me, in the 2 minutes that I have left, let me give you a couple of extra results. So we can define this Aryeh coefficient, which is the L1 norm of this square root of PQ. It's a quantity that shows up in hypothesis testing closely related to the Hellinger distance. So it clearly upper bounds the pointwise minimum, right? So we can give upper and lower bounds on this quantity for product measures in terms of the PIs and QIs. And let me finish on actually a result that's not included in this alt paper, but it was inspired by it. It's natural follow-up, and I think it's a very interesting line of work. So there's this thing called the Sheffi identity, which connects this pointwise minimum to the total variation norm between two distributions, which is just the total variation is just half the L1 norm. And again, if I were to give you two sets of parameters, two n tuples of parameters, P and Q, each of which induces a Bernoulli product measure, and ask you to compute their total variation, that problem is sharply hard. So you can do it exactly. There are various polynomial time approximation schemes. Now, if I asked you for trivial estimates in terms of the P and Q, so an obvious upper bound is the L1 norm between P and Q, and an obvious lower bound is the L3 norm between P and Q, right? And that was kind of, and they have a gap of n, a multiplicative gap of n in the worst case. So what I discovered last summer is that actually a lower bound can be sharpened to the L2 norm of P and Q up to some constants, but universal constants. So actually, the lower bound is not L infinity, but L2, which is much better. It cuts down the gap from n to root n. And actually, that's the best you can do if all you're looking at is the difference between p and q. That's the best you can do. You can't do better than this root n gap. And in the symmetric case, in the case where p equals 1 minus q, actually an upper bound is exactly p minus q, the L2 norm. So in some sense, it's kind of surprising because when you think of the L1, the Kontorovich norm, you think somehow it should behave like L1, right? Morally, but actually it behaves in some sense more like L2, which is kind of surprising. That's it. I'm done. Thank you.
So in the last result, like P encodes the product matter is like a P1, P2, P3.
Yeah, P and Q are both vectors of n parameters, and then this is the product measure of Bernoulli of P1, Bernoulli of P2, Bernoulli of P3. So these two are product measures on the binary hypercube.
And if we compare it with something like say jumping from TV to like something given by Pinsky, like
Yeah. Right. So the problem with Pinsker and Hellinger, there are various bounds on L1. The problem is take any pair of bounds of this kind, take the lower bound and the upper bound, the ratio is unbounded in the worst case. So if your goal is to have bounds such that the upper bound divided by the lower bound has a bounded ratio, I think this is the only thing that was known. All the other stuff, but really, I went through the literature, that all other stuff has upper bound over lower bound blows up, not even bounded. Yeah. They blow up. I mean, they're good in some regimes, but overall they blow up. So this trivial thing is the only thing that, as far as I know, is the only bound that didn't blow up.
Blowing up with respect to what?
Just P and Q. So take the worst case. Yeah, take the worst case over P and Q, and for even for n equals 1, I think. So really blows up in every dimension.
There's no way to estimate the best constant here?
No, here?
Yeah, like no, in the sharpness.
No, I gave a constant. I have a conjecture about the best constant. There's a small.
It's one?
It's not one. It's like no, it's not one. It's like 1 over root 2 or something. It's small. It's reasonable. It's not crazy, but it's not one.
Any other questions?
By the way, this result was actually somebody at this conference is using this result in one of their talks. Who is? Yeah. You'll see later. Yeah, I should have mentioned that. Yeah, this result is not from this paper, so I'm just tacking it on as an extra. But yeah, I published the paper in the summer, put it on archive, and like a month later, somebody was using it in an alt paper. So you'll get to see it used later on. Yeah.
So let's
So like you consider the difference of the probability of y different per different, basically a sort of misclassification. Like have you consider other kind of laws, like other kind of distance y?
Like I guess KL would be most natural, right? KL divergence or something like logarithmic loss, right? Yeah, it will probably lead to, so KL, the nice thing about KL is that it tensorises very nicely. So, yeah, total variation is actually a nasty kind of analytically not very tractable quantity. So, yeah, it's kind of, fact of life.